everybody. This is Paul Taubman with 9.connects. You are in the right place if you are here for our webinar on translation, EDA translation in particular. And we have quite a bit to cover here today. So I'm going to get right into it here. Got a couple of objectives for today. First and foremost, I want to talk about starting with what you got when it comes to translation. That's a really important element of this. If you think that it's one size fits all, well, you're kind of going to be in for a bit of a surprise. We're going to walk through the Beaglebone blackboard. And so we'll take some look at that, and we're going to show you a procedure that we came up with. It's not set in stone, but at least it'll give you an idea of some path to take if you are going to take on a translation, or what we have to do when we take on a translation. And then some final thoughts. You're going to see some interesting oddities and things that we come across, and they're just going to happen because translation, just like we went to at the very beginning over here, if I jump back up here, you know, this was a translation between English and Russian and back into English again, right? And these are the kind of weird things that you get when you start bouncing between two different languages that have two different structures, and the same thing is true in EDA as well. So with that being said, one quick housekeeping note. I might have some time for some questions. If not, feel free to write them into the question panel of your GoToWebinar panel. And Christopher's also on the line with me over here as well, and he should be able to answer a couple of questions because we do translations quite often here at 9.connects. And of course, if we can't get to those questions, we will answer them through an email after the webinar. Do want to start off with a polling question though. I'm kind of curious to know, since this is kind of an interesting way of design, what frequency do you translate files? So if you can take a moment to answer this polling question, I'd appreciate that. Okay, so our results are in there. Hopefully you can see them here. So a good portion of you are doing quite a few of these translations every year. So I appreciate you guys giving us that feedback because we really didn't know what to expect from this polling question. So very interesting data. The second thing is we got one more polling question for you. I'd like to know why you're translating these files. Okay, so again, hopefully you can see the data over here. It is 66% of you, almost pretty much 2/3 of you are actually doing this because you're going between EDA tools. And there are layout services that are being done there as well. And also you do find projects that are cool but need to be translated. And for the 10% who are here, who don't translate but here to learn, thanks for joining us here today. So with that, let's talk about some ways of converting designs. Believe it or not, most of the time when we get stuff here at 9.connects, we have to draw the design again. We are given PDFs of the schematics, we are given Gerbers and manufacturing documents, and more often than not, what happens is that the source files are missing. This happens quite often when you've had a company that went through several mergers. They didn't necessarily have a great document control system. And as a result of that, this is what they've got. They were able to salvage this and they say, can you basically get us back into an EDA tool? So this is a very viable option. We do it all the time here at 9.connects. A second way to do this is to create a parser. You basically write up a parsing code to translate. We rarely ever do this here at 9.connects. You have to have readable source files to do this. So if it's encrypted or they're in binary, that's going to be a big problem to start off with. You have to understand both the source and the destination formats. And lastly, you've got to be well-versed in a programming language. So for example, where we do actually use parsers here at 9.connects is if we're going between something like Altium Designer and the Allegro Sigrity tool for one of our customers who's looking for some type of basically some type of simulation between the board and, well, actually they're just looking for simulation on the board. And the reason we do this is because we do have readable source files, which are usually our manufacturing files, and we do enough of this to justify the writing of the code for this type of work. So as opposed to having to sit there for hours and trying to import stuff manually into the Sigrity tool, it just made more sense to create a parser for that. But for the most part, we wouldn't do this over here unless it was an absolute last resort and we had like 50 files, let's say 50 projects that we would actually have to translate. Most of the time, we'll just draw it again. So another thing that you might have is the ability to export from one tool to another. Well, to be perfectly honest with you, it's really rare to find an export tool to do this. And that's, of course, because we're dealing with a saturated EDA market. And at this point, very few people are either using Visio or AutoCAD for their drawings. They're more than likely using an EDA tool. So now with everybody having an EDA tool, the question is, can someone take more market share from someone else? And believe it or not, this is where you start seeing import and export tools come into play. So for example, EDA tool companies don't want to lose customers. So that as a result of that, they're not going to put in a format that easily allows a competitor to take their information and translate it in. I put this down here for a moment, but let me explain this a little bit more. But there is another element to this, and Altium's actually done this, to strategically capture a piece of the tool chain. So what do I mean by that? Well, I'll give you two examples. In Altium Designer Schematic, you can actually export to pads, and you can also export to OrCAD. So pads is a Mentor product, and OrCAD is a Cadence product. So why did they do that? Well, it comes down to this thing about the tool chain. We're very familiar in Altium that everything's integrated as one. You have a schematic side and a PCB side. You don't have to deal with two tools. However, if you're using pads or using OrCAD, you're using what's called the classic tool chain set, where you have one program that handles the schematic side and you have another program that handles the PCB side. And in many cases, they weren't necessarily developed by the same software developers. It could have been through acquisitions or mergers. So what Altium felt was that, well, maybe I can't get a whole piece of the pie of that customer who has these products, but maybe I can get the schematic side of it. And so that's why they did what they did over here. It was really a strategic effort to try to grab a little more market share from these two organizations. But for the most part, let me just go back to this. It's not easy to find exporting tools. Okay? Most of the time, if you're going to do this, and assuming that the tool has it, you're going to be importing from one tool to another. And of course, this has its fair share of issues. And by the way, this is where we're going to focus most of today's webinar on anyways. So within a given tool, each translator is going to be written separately. So let's say Altium has one for Zukin, and they have another one for Mentor Graphics, and they have another one for Allegro. They may even have one for their own PCAD as well. But all these had to be written separately because they're parsing different files. They're different architectures. So it can't be a one size fits all. Another thing is it's based on what the programmer has available. So if I was tasked as a programmer to write a translation, well, what would I need? Well, first and foremost, I kind of need to get access to the competitor's tools, all right? And most of the time what these guys will do, because obviously they're not going to sell it to each other, they'll talk to maybe one of their customers who they happen to know has the competitor's tools, and they may do some type of third-party contracting through them. The second thing that they're going to do is they're going to design the files. You need design files from the competitor's tools. You just need to say, okay, well, what am I starting off with? Because I need to ultimately know how I'm going to translate it. And then lastly, you got to have the manufacturing files, because you got to be able to compare what was originally done to what you have now. And if you think about it, given the time frame, you're not going to get too many examples of this. So they may only get about 2 or 3 different examples. And as a result of that, certain things can be missed. So if a company comes out and says, we've got a brand new translator that can do it for X, Y, and Z, don't be quick to jump at it, because more than likely you're going to be the one helping them to debug it, because they only had so many samples to work with. The other things that you got to worry about is you have to export through an ASCII version of the file. So most tools basically save their stuff in binary to begin with. So if a customer comes to us and they say, hey, can you bring this into, let's say, Altium, then the first thing we got to tell them is like, hey, you got to make sure you save these files off as an ASCII version of it. And a lot of the tools don't even want to do that anymore, because again, they don't want to see their stuff getting migrated to another tool set. So here's an example of them. Not all of them will be available in ASCII. So Altium's library files, for example, are not available in ASCII, much to our dismay here at 9.connects, because we could do some cool things with them if we could gain access to their ASCII files. But nevertheless, they don't allow that, so we have that limitation. Another thing is to find the right version of the file to export. So formats do change. And why do they change? Well, there's several reasons. Obviously, they don't want to see their stuff getting exported or imported into other tools, but also because they're either adding new features, or in some cases, those tools want to force their customers to bump revisions, because obviously when they upgrade, there is residuals to be made from that. So that's what they're trying to do a lot of times with these format changes. If a change does come, well, then it's usually 6 months to 2 years catch-up time for these translators to pick up on those changes. And you got to remember something, and this is kind of unfortunate, but this is the market that we're in. This is not, these abilities to import and export designs is not based on engineering need. It's based on market. and it's demands of the customer. So if a tool company says, you know what, we can grab about 5 to 10% market share from this other company here, then they might invest in this. But later on, once it's been developed, if there's only maybe a 1% pullover from there, they're not going to really put the time and the effort into this because they want to put it into other tools. Remember, there's only so many programmers, there's only so much time, and there's so many great ideas. So that unfortunately, translators are based on market demand. Okay. So let's assume that we actually got it in. Let's say that we used an importer tool, it worked, and sometimes they simply just don't work, but let's say we got it in. That's not the end of the story, that's really just the beginning. And so what we want to do now is we want to talk about this mess that we do need to clean up. And so what we did was we searched for an open source board, and we found one from beagleboard.org. So they have a various line of product, but they put their stuff out as open source. This is known as the Beaglebone Black. So I think they just use the black ink in order to represent this, but they have like a Beagleboard blue, and I think even a red. They've got a number of different products out here, but this is the one that we happen to pick. It is open source, so we're not taking something from them there. This is the B6 revision as far as we know based on their website. This is the latest and the greatest, and these happen to be Allegro OrCAD files. Now, when we originally wanted to do this webinar, we also actually wanted to pull something from PADS because Mentor does have a version of the Beagleboard also available as an open source. What we found was that they have an older version, and if we start mixing and matching versions between the schematics and the PCB, well, number one, it just makes a huge mess. And number two, that's not very realistic. So most of the time when we have someone asking us to do a translation, the schematics and the PCB do match with each other. So we're not dealing with revision mismatches when we do these translations. And so that would not be a real use case if we were doing that situation where we're dealing with a schematic of one revision and a PCB that does not match up with it. Okay, so with that being said, let's get out of the slide deck here and let's jump into Altium Designer. All right, so here is the Beagleboard, and what we have done here is we have imported it in. So if you're going to do an import, it's going to be a file, import wizard, and you'd go through the motions of that, and this is the end product of it. What we're going to do over here is we're going to go through an action item list, and if you look on your panel for GoToWebinar, we have provided you a PDF, and this PDF I am going to be following here so I don't have to jump back and forth between my slide deck in order to talk about each one of these items. I did put this together a few days ago. I'd call it Rev A. With any type of Rev A, it's going to be short-lived because there'll probably be a bunch of changes to it, and I talk about here in the list. But the idea here was to just provide a systematic procedure so that we don't jump the gun, we don't make a mess of something, that we don't have to start over again. And that's what we've got over here. So take a moment to pull that down. And while you're doing that, what I'm going to do is I'm going to start with the first action item. So the first action item on this list is to check designator annotations between the schematic and the PCB. What do we mean by that? Before you want to begin anything, you want to make sure that the designators on the PCB side match the ones on the schematic side. And many times in a tool chain, what happens is that something got pulled from the schematic side to the PCB, there was a re-annotation done, and that re-annotation did not make its way back to the schematic. And if it didn't make it back, that needs to be resolved up front immediately. Now, how do you do that? Well, there's different ways. One way is to basically, you could print out bill of materials on the schematic side and the PCB side. And actually, when we go through this, you'll see that we do that in certain instances. But a faster way to do it, at least in Altium Designer, is if you go into project and you go into your component links. So project component links, and this has to be done on the PCB side. And the component links here is really powerful, and it's really for the purposes of creating what's called unique IDs. But what this also does is it gives you a sanity check to see what on the schematic side needs to be matched up with the PCB. Now, right now, we've got 3 columns, and what we want to do is ultimately get this mess over here on the left side into the match components on this side here. What we see in the very first column are those schematic symbols that currently Altium does not recognize an equivalent PCB on the PCB side. In the middle column, we have footprints where it does not recognize the schematics on the, or symbols on the schematic side. And what we want to do is we want to match them together. So the easiest thing to do is just match pairs by, and you'll see the designators are already turned on. So if we click on this over here, we've got some good information. We got some good news and we got some bad news. The good news is that we have no residual information sitting over here. Okay, so there's no schematic parts that somehow still do not have footprints associated with them, and we have footprints. We do not have footprints that have no symbols associated with, if that makes sense. What we have is a complete matchup. That's a good sign. What we also want to look at here is how they got matched up, and are they actually matched up to the same thing? And you can see we do have a little bit of an issue. So here you can see that the footprint is different, where this one's calling for an R40, it's really an 0402. This one's calling for an 0805. But if you do look at the parametric information, basically the value and its voltage limit, these are the same. Okay, so this is a good sign that these do match up. And if I want to, I can perform the update, and as a matter of fact, I will. I'm going to say two other notes here just for your information. So why does Altium even bother with this to begin with? What impact does it have on Altium? So Altium uses something called the unique ID. And Altium Designer 18, they hid the unique IDs. In the past, you could see them. They knew people were playing with them. It messed things up. It caused a lot of support issues. So they basically hid them as of Altium Designer 18. But what you're really doing over here is creating the relationship between the C1 symbol and the C1 footprint, and so on and so far and so on for each one of these. And that's the whole reason that you're doing that. And behind the scenes, it's a unique ID, so that if you do a re-annotation, Altium just looks at the unique IDs and not the designator. That's why you're really doing this. But it certainly helps with the net list, and we can definitely perform the update. And the links have been modified. It has no graphical impact on the schematic or on the PCB. It's really just assisting Altium with its net list control between the schematic side and the PCB side. So that's point number one. The next thing we would have you do is we want to make a footprint and a schematic library. Those can be done under Design, Make PCB Library, and then we'd go on to the schematic side here. And again, we'd go under Design and we'd make Schematic Library. In theory, you could make an integrated library. There's really no reason for us to do that right now because A, I'm not really sure what we were going to get out of it, and B, all we're going to do is extract it and get the PCB and the schematic out of it anyway. So right now, all we just want to do is just get those two individual libraries. Later on, we will have to do a bit of cleanup, especially on the footprint side. Okay, so that's the second thing we would do. Number three, what we want to do is get all the stuff off the absolute origin. So let me go back to the original translation here. What's going to happen more often than not is that Altium is going to stick it on the absolute origin, which means that if you're trying to select something, and hopefully you can see my screen here with this green shade, it's not allowing me to go down, and it's not allowing me to go into quadrants. If you think of this as a Cartesian plane, it's not allowing me into the second, third, or fourth quadrants of this Cartesian plane. So I need to move it. What can we do with this? Pretty simple to move it. Oh, there we go. In fact, I selected it. That's why it's taken a moment to think. Let's zoom in over here. The first thing that I would encourage you to do is to make sure that you put some type of marking on the absolute origin. The reason why is that after we move this, then we're going to have to move the origin as well. So that's why I want to do this. The second thing we'll do here is we're going to zoom out a little bit. Make sure all of your layers are turned on, all your mechanical layers, anything that's associated with this project, turn them all on. And at that point, we can now do a Control A. That is a universal command in all software in the PC platforms. It's basically a select all. From there, there's different ways of moving it. So the way I'm going to do this is I'm going to hit the M key to move. And so I'm going to do move selection. I'm going to click down. And I'm going to drag this in such a place that I know for a fact it's going to be away from any of the edges of the other areas of the Cartesian plane. And so I won't have a problem dragging and selecting. So I'll move this over here as such. And again, you're going to see it's going to take a bit because there's a lot of primitives that are on this particular board. So, and of course, you got to remember something, that Altium, below all of its, below the skin, right, below the GUI interface, really actually is a database. So each one of these little parts that are in over here are being represented as a part of some type of database within the file system itself. These have now been moved. So what do we want to do now? After I deselect it here, I'm going to zoom in here and I'm going to fix my origin. That is going to be under Edit Origin. and then we will do a set. So it puts on my cursor, and I'll drop that in, and now my origin is set to go. And of course, we can move this around to wherever we need to, but I just want to be in an area that I know I'm not going to have a problem selecting things. So that is the next thing that we want to do. Number 4, we're going to turn off the design rule checker. There's a ton of errors that are going to come up. That doesn't surprise me. One of the things that I always thought was kind of interesting about most translations is that not all the rules come through. So Altium defaults to its rules, and as a result, we get a lot of green here. And this right now is just a bit of an eyesore. So let's not deal with DRCs for the moment. We will get to them, but let's get them out of the way for the moment. The way we can get to that is we're going to hit the little cog up here. That is the PCB, that is the Altium preferences. Under the preferences, you go to the PCB editor, and under the editor, we go to the general, and we want to make sure that this online DRC is turned off. Now you can see I was doing a practice session, so I already had it turned off. You normally want this on. If you're doing a new design, you want this on. For translation purposes, for the moment, I want this turned off. So that's what we're going to do here. So I'm going to press OK. If they still happen to have any residual green here, you can always go to Tools, and we can reset the error markers. Okay, so we've got that kind of out of the way, so it's a little bit easier to look at. The next thing we want to do is we want to check the layer stacks. We want to know if we got planes, are we dealing with polygon pores, what's our situation? That's going to be under Design, and we're going to go into our layer stack manager here. This will take a moment. And of course, if you're familiar with Altium, you have single layers and you have plane layers. And a lot of people these days don't really use the plane layers because the polygon pores offer a lot more flexibility. And you can see over here, this is a 6-layer board. So we have our 6 layers. That's what the 6 is representing here. And they are all signals. So we are definitely going to be dealing with polygon pores for this particular design. Not a problem. People just, that's what a lot of designers do, and that's to just be expected. Okay, so we know we've got what we're dealing with in terms of the layer stack. Number 6, preliminary mechanical layer cleanup. So if some of this stuff can be removed, you want to remove it, because again, all of these things are little primitives, and even though they're not necessarily important to the manufacturing of the board, like in terms of copper, like the actual fabrication of the board, they still are considered primitives, and they are definitely taking up space, and the response you can see has been a little bit sluggish because of the number of primitives. So if I want to get rid of a few things, let's say for instance this assembly here, maybe I want to use Draftsman instead later on than to keep this. So I have some options. One option is to copy this and put it into another PCB dock. I could turn it off, but again, it's going to retain this information in the database, making things kind of slow. Or I can say, you know what, I'm going to remove this altogether, and later on I'll handle it in Draftsman. So any way you want to handle it, you can do that. One of the ways you can find out where you got things, if you zoom into something and you click it, double click into it, you'll get its properties. You can see which layer it's on. In this case, these are all assembly. Now, if I want to just get rid of the assembly layer, well, the easiest thing to do is go into View Configuration, find the layer, right click, and delete the layer. And I will wipe out that layer. So make sure if that's not a layer, if it's a layer you need for some reason, you're going to have to leave it on, okay? But in this case, I'm just going to remove it. And so now that layer has been removed. Of course, you do want to go through all of these to understand why they are there. The one thing, and this again goes back to translations between, like, you know, if you use the analogy between English and Russian, for example, the Allegro tool actually has very defined layers. They have a set for boards, they have them for components, and I think there's a third one as well. Whereas Altium has been starting to get down that path where they have started to declare certain mechanical layers to have a certain type of feature associated to them, like 3D bodies or assemblies. Most of the stuff is still going to end up over here, and that's what you see. Some of it you may need, some of it you may say, forget it, I've got my own stuff. It's going to be up to you as to what you can and can't, will or will not delete. Let's put it that way. There's one other thing to mention here too. You're also going to find out very quickly what layers you will not be able to delete because they are associated with a component. So let's take an example over here. If I was to go over to our assembly top and our assembly bottom and say, you know what, I don't want these on here right now. They're, you know, for whatever reason, I just don't want them. You can right click here and you can delete layer. But the minute you get this, what this is telling you is that, look, if you want to really get rid of this layer, you're going to have to do something about your libraries first. And we will talk about that in a bit, But what this is telling me is that for now, if you want to get rid of this, you're going to deal with your libraries. We don't encourage that until later on because there's other things we want to fix first. The best thing you can do if you really don't want to see those is just to simply turn them off for now. And that's what you can do. So that's going to be your initial effort there, is just to kind of clean up these layers, which layers you want to keep because they've got good information you don't want to keep because either it's not pertinent to you or it may just simply something you can do in Draftsman. After we've done this over here, the next thing that we actually want to do is we want to clean up the continuity issues. So we need to take a step back here and think of translations being very different from regular design. If you're familiar with regular design, one of the first things we're going to do is we're going to go in, we're going to set up the rules because we want to say, hey, we need to set these things up so we don't create things that we can't manufacture. Well, 99% of the time when we do a translation, it's already been manufactured. So what we're not going to try to do is change the copper on the board. What we really want to do is make sure that we understand where there's copper where it's supposed to be. And if there's copper missing, we need to understand why it is. And for the most part, it's usually due to polygon pores that are missing. So what can we do here? Well, I'm not going to run this through the DRC. What I'm actually going to do is I'm going to turn on what they call the rat's nest. Altium does not use the term rat's nest. We're going to go under View, Connections, and we are going to do Show All. So we're going to start seeing the rat's nest or the connection lines all through this here. One of the other things that you could do to kind of put yourself in some type of place where you're not looking at something, a big mess like this, is you can do Shift S. This puts you into single layer mode. So it gives you an idea each layer of what you're kind of looking at. Now, as I mentioned, most of these continuity issues are going to are really dealing with polygon pores, and that's what we want to fix. Now, one of the things you'll notice, if I go over here into Tools and I do a polygon pore, okay, now let's do a repore all. So, I mean, that would be the logical thing to do. Now, some of them come up, but we know that there's ones that are not here, especially on layer 2, because layer 2 is acting as a ground. In fact, it says that layer 2 underscore ground. Or if we go to layer 5, it says underscore power. So we do see that there are other polygon pores here, but they're not pouring. So now we need to investigate why that is. And just to give you a heads up, this actually took us about an hour and a half to figure out what was going on. So you will get into these weird situations like, why is this thing not pouring? If I click on this, or how do I even click on this one when this other one over here seems to be overriding everything? So I'll give you a little hint about this particular board. What they did in Allegro apparently is that they drew out all of these individual polygon pores. And then for the top one, they flooded it, but then they somehow put in what they call a polygon cutout to prevent the top one from flooding over all the other ones. And so that's actually what happened over there. And how do we know that? Well, we've got little hints here. In fact, what I'm going to do is I'm going to shelve this first one. So I'm going to right click and I'm going to go into my polygon actions and I'm going to shelve the selected one. And then you'll notice these dashed lines. Well, that's a hint that we actually have copper cutouts, polygon pore cutouts over here. So yes, I can select this one now because the top one is now moved out of the way. But now if I try to pour it, so if I go into right click polygon actions and I try to repore selected, it still isn't going to pour it. So now I've got to, ultimately what we found was that these cutouts are causing the problem. So we were deleting these. So here's the first one, and we found there's actually 2 of them there. Okay, so I don't know if that's actually a procedure in Allegro, and that was a translation issue within Altium. I'm not sure what happened over there, but we got rid of these 2. And if I right click and say repore all, polygon actions, we'll do a repore all. I now get the pour that I want. Well, I still have to bring back my other one here as well. So I'm going to right click here and go into polygon actions. And let's see, I can't do it there. That's fine. We'll go under Tools, Polygon Pores, Restore Shelved Polygon. And there it is. And of course, if I want to repore this one, I can. So under the polygon pore action here, we will repore the selected, and there it is. So in Altium, we really actually did not need to have the cutouts in this particular instance. So probably in Allegro, they probably needed them, but for some reason, Altium, we were able to do this because basically we already had the other polygons, and those other polygons are forcing the one on the outside to pull back. So there you go. I do have a polling question for you before we continue here. Are you interested in learning more about polygon pores for a future webinar? Okay, so about half of you said definitely, and as we go down the list, it still looks like, it sounds like if we actually did one here, you would attend it, so for the most part. So we'll definitely keep that in mind. Thank you very much. Going back to our polygon pour here, we would have to do this for each and every single layer. Just because I did a repour all doesn't mean that layer 2 got repaired. And so that's what we had to do. We had to go through all of these, clean them up, remove things that weren't supposed to be there, and basically get those polygons to pour, and the connection lines would ultimately disappear. And that was a good thing. There's another thing that we would do too, because at the end, after we poured all the polygons, what we found is we still had a few connection lines left. And that was because we have to make some modifications to the rules. If you're familiar with polygons, polygons are driven by 3 things. It's properties, the polygon pour connect in the rules, and the clearance rules. Those are the 3 things that drive it. Sometimes it's not obvious here as to what the rules ought to be. And so what you can do is you can go into File, and you can go to Fabrication Outputs, and you can create the Gerber files or a Gerber file for the layer that you're on. What we did was we actually pulled in the original artwork so we can compare it. So I'm going to go over here to the CAM tool. I'm going to hold down my control key and I'm going to scroll down. So this is Camtastic. You don't have to be an expert in order to make use of this. If you used it to generate Gerbers within Altium, it's automatically going to pop it up. If you want to add more, like this artwork that came in over here, or this artwork that came from another one of the versions, you can do that as well. It's really just doing a file import. Don't do a file new or file open, because it'll just create a brand new CAM. If you want to get into the existing CAM, you've got to do file import, click on Gerber, tell it where it is, press OK, and trust me, it'll do pretty good with it. There's not a whole lot of modification. The other thing you're going to need is the Camtastic panel. That should come up on its own. If not, go to the far right side and pull up the panels to get it. So you'll see over here on the top here, these were the, this was an experiment that I was running with a clean set. What you see with the .art files, those are the ones that actually come from Allegro. And then you can see this one down here on the bottom, this comes from our original translated board. So really what I want to do is turn on these 2 layers, pretty simple enough to do, and I want to compare them. So the red here is the original artwork, the yellow here is my artwork, so I can compare what I'm seeing against it. And if I started seeing red in the middle over here, that would indicate to me that I probably need to change my rules so that the polygon pour will pour into this area and make the completed copper necessary to complete my my wiring or my continuity on those signals over there. And by the way, the simplest thing to do here, if you want to see this one on the top, you can do this. So if you want to compare to see if Altium's actually putting additional copper where the original Gerbers did not put it, you can compare it that way as well. So it's just a matter of clicking on it to make it whatever layer you want to be on the top and the bottom. One other quick note, because a lot of times if you say, well, yeah, I see that over here, but I need to know the clearance. So by the way, navigating this is basically the same, very much similar to Altium, but not completely the same. You can right click the pan, you can hold down your control key to zoom in and out. So I'm going to zoom into this little XY area in a sense. So if I wanted to measure, for example, the distance between these 2, just to get an idea of, actually, in fact, I want to do it here. Let's do a control here. I want to do it on this black area here because I want to see what this original clearance is between these. So if I go here to the analysis, go to measure, and I go to point, and I'll click once here, and I'll go click here on the other one. And I probably should zoom it in a little bit better, but then I can see the distance here. So this looks like possibly, well, it's diagonal, but it's probably about 6 mil. So I can certainly zoom this in over here and get a better or accurate shot of that. And when I'm done, I can right click and cancel the action. So very quickly, I know I went through that a little bit fast. If you want to see that again, go to analysis, measure, point to point. You can do Shift M2, which does the same thing in the PCB dock. And then from there, you just click your 2 points. And there you go, you get your number. And you can keep on doing that. You don't have to until you right click and escape out. So it's a little bit different from the other editors in Altium. Okay, So that's another way we would use to finish the continuity. And by the way, at the end, and I'll kind of jump to one of the steps here, after we are done with everything in the boards, we take the original Gerbers and we compare them against the ones that were of the end product that we did in the translation and make sure that they're one-to-one. So this is just a rough cut to make sure that we've got our continuity, but in the end, we do check them again to make sure that everything else matches up. All right, so that was the resolve continuity issues, that's polygon pores, and then checking the Gerbers. It takes us to the next step there of number 8, of the cleanup of the DRC. So let's go back to our original board here. And the easiest thing for me to do at this point is to basically just run what you got. Go into Tools, Design Rule Check, change this where it says stop when, 9,999, that's the most Altium will do anyways. Hit the Design Rule Checker and let it have at it. From there, you're going to see where the messes are. Most of the time, for example, in the clearance rules, what you're going to find is that the clearance rules didn't get changed one iota. And if we look at this, for example, you'll see that the clearance constraint here is 10 mils, all. If we go into our design, or pardon me, our rules, bring this back here. So we go into design rules. And if we look at our clearance rules over, here's our clearance rules. You'll see that the default generally is 10 on all of these. That's what came in. Well, obviously that's going to be different. So you want to start looking around and seeing what the general clearances are on the board. And even the Gerber files will give you a hint at that as well. That's what the measurement tool is going to do. Again, the intention is to match it up, match the rules up with the existing board where the copper is correct and it's already been manufactured. So you'd want to find things that would fix that. And what you're going to find more often than not is that once you tweak one of these things, you can easily fix 2,000 to 3,000 of these errors here. Now you will want to keep running this because remember the count total was 9,999. That's all Altium allows. So you may have fixed 4,000 or 5,000 of these here, but that may introduce more of them here because not all the rules got ran because it already hit its upper limit in terms of the number of violations it's going to allow. So that's what you're going to do. You're going to go through those and ultimately clean them all up. And so there you go. Now that you've got that cleaned up, you'll notice one thing, by the way, up to this point, we've done nothing with the schematics. And again, it's weird for us who do our design when you're doing a new design because the schematics drive the PCB. But again, because this is a manufactured board, it's actually the PCB that's going to drive the schematics. So now we've got the PCB set up over here, and now we're going to start getting the schematic connected into the PCB. We want to get the netlist copacetic with each other. So if you look at that, we have number 9 there, and we break it down into 9A, 9B, and 9C. But if you really look at it, component links we've already done. So that's just the first, that's a step that should have been done from the get-go, and probably in a subsequent revision of this right up here, I'm going to move that component links to step number 1. But let's go over to 9B, which is the electric rule checker, the ERC. So the ERC, we need to go over to the schematic side. And for that, we would simply right-click and say validate PCB project. It used to be compile in Altium Designer 20. The compilers have been changed up a little bit, so now they give you the ability to validate it on the fly by clicking on the validation. And you'll want to check these messages here. Of course, some of them either you're going to fix or you're just going to justify, saying, okay, I'm cool with the no driving source stuff. It's not going to have a huge impact on me. You may want to turn off the rule, or you may want to actually change it so that these violations will go away. I'll leave it to you. I have different opinions about why you should and why you shouldn't do those things. I don't have a definitive opinion on that. As for the rest of these, I'd want to know why there's multiple names. More often than not, that's because in Allegro, again, you've got your translation differences, where in Altium Designer, there is no property name to a wire, whereas all the other tools have that. If you go into Allegro, you go into pads, you go into DX Designer, you go into a wire, you can give the property of a name and you can turn it on. Altium doesn't have that. It separates out the net name or the net label from the wire. Okay, so as a result of that, you may get something along the lines of a power symbol being on a wire, but then Altium turned on the wires when it was doing the translation, basically created a wire net name and slapped it on the wire. And now you've got a conflict. That's really what happened there. And so you want to resolve those type of things in there. So let's just take a look at the schematic. Let me make sure we've got those things. I don't want to jump the gun here in my list. So that's the one thing, is the electric rule checker, the ERC. The next one beyond on there is just to do a brief ECO to see what the differences are between the schematic and the PCB. So we're going to go to design, and we're going to go here to update the PCB doc 0, because this is, again, the one that came straight from the translation. It's going to try to meet some net classes. I'm just going to continue those here. The intention is not to hit execute change. In fact, I don't encourage it at all. What you want to see is what the differences are between the schematic side and the PCB side. You can see we've got some issues over here. These are 0402s, and for some reason it wants to change these to 0603s. So there's definitely a problem here with the footprints. And I'm going to give you a hint here right now that the amount of time that we have spent on this particular project, the most time that has been spent has been cleaning up the footprints. And not because we're putting new ones in, but because we've got different names over here and we need to know what we really have got. So it's a huge list of what the schematic is saying, what the PCB is saying, and in a lot of cases they're not jiving with each other. That's why there's a huge modification list that is over here. Okay, and that's what we're cleaning up right now in this translation. So there we go. There's also some parameter changes, and as an Altium Designer 18, you can see the parameters on the PCB side. Okay, and that's and so you can push these over. I could push these over right now, but I'd probably do that a little bit later on. Okay, here are the net names. I prefer to use the Altium ones over the ones that were given by Allegro, because Altium does have some rhyme or reason to their net naming convention here. So I'd want to just simply push these over at some point. I won't do it now, but I would also want to understand why Altium wants to change these names. So again, this may be because there's net labels sitting on power lines that shouldn't be there. It may want to remove one of the classes. I'm not sure I want this or not. It depends on how the rules are coming out. If I use this clock class, then obviously I need this for my rules. It also is trying to remove differential pairs. So in this case here, I'd want to make sure that I added those directives onto the schematic side so that the differential pairs on my board are matching up to the ones in the schematic. It's trying to add a few component classes, some rooms here as well. These I'll probably remove on my own. These over here I might let go later on, or I could go into project options and turn those on or off. So that's what we do. But normally we would take pictures of each of these. We would not hit execute changes. We just take the pictures of those. I suppose you could also take the log, but the log really doesn't work until you execute it. So that's what we do with that here, and we would close it. So we'd go in there and make those type of cleanups. After we've got that, we actually do go into number 10, which is the schematic cleanup. So there's different things that we would clean up. So things, for example, like this deground here, we would actually have it pointing downward, not off to the side. We may also change out some of the symbols so that it looks a little tighter for the resistors, for example. If we want to get rid of these connections here, we could do that. And I'll show you guys a little trick. I don't know if we've ever done this in any webinar before, but let's say, for instance, I want to change these to ports. Do I have to go in and change these each individually as ports? No. I can do a Control-C on these. I can go into my edit. Instead of doing paste, I'll do Smart Paste. And here it tells me I've got 7 offsheet connectors and saying, well, what do you want to paste them as? Well, in this case, I want to paste them as ports. I'll press OK, and then there they are. All right, so I don't have to go in and do one at a time here. I delete those, drop them in, and continue on. You can leave these offsheet connectors. They're not a problem. It's just that they're not as robust as the ports are. So that's completely left to your devices if you want it. Okay, one of the things you better be very careful about is where these net labels are placed. And again, it goes back to that thing I was trying to explain before. Wires do not have name properties. So when Altium went in and took the name property from Allegro, it created this thing called a net label. And of course, you stick that on here and it gives it the name. Where the problem comes in is if this happens to be right over here, it's going to short these two wires together. And just to give that example, you'll notice that this wire here is called OSC. So there you go, OSC1_in. If I take this label over here and I move it here, you'll now call this one, you'll see that it's now OSC0_in. you probably should see this in the ECO as well. So if you're seeing weird things like that, that might be an indication that the net label is actually sorting things out. So be very, very aware of that one there. So those are the things that you'd probably want to go in and clean up and make sure that they're all good to go. We look at the next step, generating a bill of materials, especially if you have footprint issues. If the footprints are not matching up, then what you can do is you can go into reports, bill of materials, and in the bill of materials, you can generate one from the schematic side, and then you can do the exact same thing, because it will look the same for the most part, if you go over to the PCB side, and you also do a reports bill of materials as well. You're gonna get 2 Excel sheets. I've already kind of done this here just because I know for the sake of time, we're getting short on it. So what I wanted to do, because we saw this earlier, there's obviously a difference between what the symbol is telling me is the footprint and what the actual PCB footprint is. So I can now look at this list here and I can compare the two and see what's going on. Now, yes, ultimately I want to change these names for 2 reasons. Number one, we'd want to add, like if it's a resistor, we want to add that resistor 3D to it. If it's a capacitor, we want to add its 3D to it. So we want to separate these off. The problem is if I start changing these names right now, I'm really going to get myself into a sticky wicket. I don't want to do that. So for the time being, what I want to do is just clean these things up, and I can do that through the footprint manager. Now, when I run the footprint manager, it takes a bit of time, and because I am short on it, I've already taken a picture of it just to kind of show it to you. The footprint manager is found in the tools footprint manager of the schematic side. And you can see here's an example. This was C126, and it was actually showing the 2 different footprints that it is claiming to have access to. And I would want it to use the 0805, and I would want to remove the other one in this particular instance. Again, the PCB, because it's a manufactured file, is the driving force here on this. The other thing I'll mention about footprints here, if you're using the footprint manager for a new design, something's wrong with your libraries. Footprint manager is really, really useful for translation, where you're taking something in from other designs and trying to reconcile between the schematic and the PCB. So just be aware of that. The next steps on there, step 11, is to just modify the libraries. The footprint is going to require the most modifications to those. Let's bring up that library over here. So what do we need to fix in that library? The mechanical layers, which we talked about earlier. You want to go through and see what mechanical layers we're dealing with in the library here. And by the way, while we were doing the design, there were some anomalies that came up where we had to fix them and then push them over to the board as well. But if we don't want all of this stuff in here, then it's time to take actions to clean these things up and then to push them over. We also add in 3Ds. That's one of our things here at 9.connect. Since people want to see the 3D, we have to add the 3D in, and that takes a lot of time. Now, both Mentor and Cadence have gotten pretty good about adding the feature capabilities in for 3D, but you got to keep in mind those tools have been around for 30+ years, and that may be a new concept for a lot of companies. So it's going to take a few years before you're automatically going to find the 3Ds associated with the components in those translations. The last 2 steps make a whole lot of sense here. I won't go into any further detail in terms of just generating the manufacturing documents and then comparing the final Gerbers the way we showed earlier in the .cam file. So with that there, I know that I want to show you a few things that we came across that were important, that it's never that clean, never that easy. And I'm fairly certain there are other things you probably have come across that we didn't even come across because they're just things that just didn't happen to be as a part of that particular board. But let me jump on over here to my PowerPoint and show you a few slides of things we did come across. So let's go to the current slide here. You're going to come across errors and anomalies. So were the errors in the original, were they in the translation, or were they in the global edits? And that's really important because when you do come across these things, you got to figure out where they came from or why it was done. And so let's take a look at a couple of them over here. So here's an example of an antenna that got flagged, and come to find out this was a part of the original board. It's just a via that's sticking out of one of the pores here, and it just happened to be there, but it goes nowhere. But we did have to track it down to make sure that we weren't somehow missing copper on another layer. U4 and U8 were coming in through unusual circumstances. They were coming in with holes in them, even though this is a surface mount pad. We had to go in the library, make the changes, push them over. So that's a translation issue. Here are some interesting things that we saw. It silks on Y1 and Y2 pads here. So you can see this is where the silk was. You can see that on this board over here, a CAM engineer went in there and cleaned this up. So here's the deal. Here at 9.connects, if you tell us to translate the board and there's silk on those pads, we will leave the silk on the pads. We will tell you or inform you that you have silk on the pads, but our intention is not to fix the design. When we're asked to do a translation, we have to translate it verbatim, okay? Be careful of this, because if you're thinking of, for example, saying, well, you know, Beaglebone.org provides these files free of charge and they've been able to use these parts, you know, create their own, and I want to do this, I'll send them over to, let's say, PCB 123, where I can do it really quick. Well, what do you think you're going to get on here? Because certain fab houses are going to clean this up, and places like WYSIWYG places like PCB 123, they're cheap, but they don't do any CAM work on your design. Well, you're going to get silk on your pads. So be aware of that. Our policy here at 9. Is we do not, we will translate it verbatim. Okay, we'll let you know what we found, but we'll translate verbatim. Here's another one that's a potential solder issue. So you can see over here, there's a pour of copper. It was a direct connect. Okay, we would not do this on ours. We would definitely want to make sure there's some thermal relieves over here on this. I suppose if you're using vapor phase, that may not be an issue. However, if you're using an oven to do the soldering, that could possibly result in a cold solder joint. We're not sure. So again, we can't fix this. We would just inform the customer of that type of result that we found. We did have some issues with odd library issues here, and we had a devil of a time on this one. We spent about an hour and a half trying to get this one to work. So there was something that may have come in through the translation that didn't seem right. We also noticed that they had polygon pore cutouts over here. We're not sure if that was just because they wanted a wider area for this, or if they too were having some problems with the library and that was just their way of trying to resolve this. But this one really, we had a big fight with this particular part to get these things to fill in properly. And here is my favorite one of all. This was R99 that's on the actual Beagle board. You can see it here. It had 2 round pads, and we weren't sure why they used this. We actually pulled up it's associated to a memory. We pulled up the Micron memory data sheet on this, took a look at what R99 was associated with, and we just want to make certain that there wasn't some unusual feature that we really had to pay attention to. And in this case here, for whatever reason, they decided to put round pads in, but there's no specific reason that we could come up with when it came to this here. Okay, what are the takeaways from all of this? Well, very quickly, our cleanup time is 80 hours, and this is still climbing here. 42 different components, 381 total components. This is being done by someone who does this all the time. The individual who does this for us does these things probably about 12 times a year, a dozen times a year. Okay, we get about 1 of these per month. So he spends a lot of time doing these. This happened to be a 2-person collaboration because I was involved with the translation here as well for this webinar. I know I just threw a bunch of things at you here. Much of the cleanup that we're still dealing with at this point in time is adding and finding 3D models, organizing and cleaning up the mechanical layers, which we talked about. And the big one that's the most difficult is renaming the components, when I mean the footprints, because when you rename the footprints, now you got to get that back into the schematic, you got to get that back into the libraries, you got to get that back into the PCB. So it's going to impact pretty much all the editors, and it just takes some time to do. Other points of reference, we're currently finishing up another design for another customer. We're at 12 weeks and counting, and these are the 2 boards that we are dealing with. One's an 18 layer, one's a 12 layer. These are the number of components. They just take time to do. It's not just a simple import and be done with it. Also, tool proficiency, really important as well. Translation is just simply different from doing a design. That's really the way you can look at it. It requires different things. You got to think outside the box. As I mentioned about that one part where we were getting these weird pullbacks on it, we had to really think as to why it was doing what it was doing. You may use tools that you don't normally use. You may have to use the Gerber, the CAM tool. You may have to use some convert primitives like the smart paste. And we didn't even talk about this, but there are a number of convert features in the PCB under tool convert, and you can play with those if you want. So in some cases, you just can't get the polygon to pour properly, and it may be better to convert the polygon into a region. Okay. and of course the footprint manager, as I mentioned earlier on. So with that, I know I'm really pressed for time here. If you do have some questions, feel free to write them down. I simply won't have the time to answer any of them right off the bat over here. If you don't mind, I'd just like to talk a moment or two about 9.connects. You are here for a reason. So moving a design between two programs obviously is not trivial. Hopefully we've proven that to you here. And you want to know what it takes to import a design. So what do we provide here? We perform translations all the time, as I mentioned earlier on. We take PDFs and Gerbers, turn them into source files. We take imports and we can clean them up. We do it quite a bit. If you want more information about what we can do, come on over here to 9.connects.com. Under the Design Services menu, the main menu on the top, you will find something called Restoration of Intellectual Property. So that's what we call it. It's not necessarily a translation to us. We're restoring something that has long since lost its source files. And so with that, I know we are at the hour, and I know we got 2 polling questions. So before you run off, if you don't mind, let me get those 2 polling questions going here. So I'm just kind of curious if, would you still do translations on your own now that you've seen what you've seen here? All right, yeah, I figured that the crowd that we had over here today, given the original polls, is very familiar with doing translations. In fact, you probably could have showed us a couple of things while we were getting this webinar prepped up for you. For the 22% who would seek additional assistance, please do consider us for this. And lastly, one other polling question. And great, thank you guys very much. Hopefully you do see all of these posted over here. And so glad that I was able to help out quite a fair share of you guys here. And so with that, I want to thank you very much for joining me here today. You guys have a great day, and we will see you next month.